Hi, all, this is Mr. Yeager. We're looking at a couple last slides for AP Physics to supplement the circuit video that was already done, which is just fine. Again, you don't need to worry about the whole surge idea that's in that other circuit video for AP. But everything else with circuits is very important. There's a couple extra things, though, that are specific to AP Physics. That is, one, we do look at trying to calculate the power a bit more in a circuit. And again, in relation to power, power is related to brightness of the bulbs. More power means a brighter bulb. Okay, always, always, always. So we already mentioned that. So if any problem is ever asking you to justify why the brightness is doing what it's doing, you have to talk about power. Okay, power is what makes it bright, not voltage, not current. Obviously, those can affect the power, but then it's the power that affects the brightness. And we'll go through when I need to add my pen in just a second here. The big thing is, if you ever want to find the total power of a circuit, all you need to do is add up all the powers of the components. Okay? You can obviously, if you wanted to, the total power is again coming from the battery, so if you know the total current and the total voltage, you just multiply those two together. But the kind of neat thing about power is it doesn't care about what type of circuit you have. You just simply add up all of the powers. It could be a mixture of series or parallel. You know, it could be series, it could be parallel, it could be a mixture. In the end, you just add them all up. You don't care at all. The big thing, though, like I said, is justifying power. So sorry, let me do one thing real quick. Add my pen back here. All right. And I was saying this in another video. How do I justify the power in a circuit? Or why would I see the bulbs change? So for example, we talked about in series. If you increase the number of bulbs in series, you're going to decrease the brightness. Now, why is that? How can you justify that? All right. So what we would go to is, this would be the primary formula to use. I think this is the easiest formula to describe power with. Instead of P, I know a lot of students, not a lot, but a number of students will ignore me and just go with P equals IV. I'm going to tell you, P equals IV requires you to say more and explain more than P equals V squared over R to get the same answer. Okay? So, let's think about it. If I have a series circuit, and then I add another bulb, well, the thing is, what happens to potential difference voltage in a series circuit? The voltage gets split up amongst all of them. So if I add another bulb, we're going to say, basically, the battery is staying the same. I didn't say I'm changing the battery, so it's still the same amount of voltage coming out from the battery, but now it has to be split up even more. So what happens to the voltage? It decreases. For each, this is talking about each light bulb's voltage decreased. What does the resistance do for a light bulb? The answer is nothing. You don't change the light bulb's still the same thing, so the resistance stays the same. So if I decrease the voltage and resistance stays the same, I decrease the power, which decreases brightness. All right? That's it. Exact same explanation goes with parallel. If you add another bulb in parallel, we said it doesn't make a difference. That's because in parallel, if I add another bulb, the voltage remains the same, the resistance of the bulb remains the same, so the power remains the same, which means the brightness stays the same. So everything keeps staying the same. My concern is, again, some people will go to P equals IV. And they'll go, well, why can't I just say the same thing? If in series, I decrease the voltage, so the power decreases. The thing is, if you add a light bulb, does the current stay the same? And the answer to that is no. The current changes, which means you need to explain what happens to the current and how that might affect, if the current changes, that could affect the power. And so that's where you got to be very, very careful. Most students do not. I have a couple. Some are sitting there. Some will figure out the voltage will decrease. The current will also decrease. Okay? Because you have more resistance. And the thing is, you'd have to explain that. You can't just sit there. The current decreases as well. I would want to know why. Why would the current decrease? Not because it splits up more. It's because the resistance increases, and therefore the current decreases, which also supports this. It just goes on and on. So all I can do is extremely encourage you to use P equals V squared over R to always explain brightness of bulbs. It's just so much easier. All right, less mistakes. All right, you can get a lot of points with P equals IV, but students never get all of the points. A lot of students get all the points with V squared over R. All right, so the last two slides are basically saying, what are you going to have, like, how do we justify why the current does what it does in a series versus a parallel? Why does the voltage do what it does, the potential difference do what it does in a series and a parallel circuit? So we have two rules which we call the Kirchhoffs Laws, or Kirchhoffs Laws. Okay, they're Kirchhoff. There's all sorts of different pronunciations for them. And the first one is called specifically the junction rule. And this one relates to current. So one other thing is to make sure that you get the correct word with the correct measurement. The junction rule refers to current. And what the junction rule basically states, which we talked about some before, is essentially saying the current that goes into the junction is the same current that goes out of the junction. I mean, you know, that's going, if I have a parallel circuit, because parallel circuits have junctions, the idea would be, we said the total current goes into the junction, but then it splits up into two separate currents, two separate smaller currents. When it comes back on the other side, how much comes out? All of it. But the thing is, why? Again, it's called the junction rule, but why does it stay the same on both sides? And it goes back to relating to the idea that there's conservation of charge, and that's what you would explain. You would explain series, the current stays the same everywhere because one, there's no junctions, and therefore charge is conserved throughout the entire circuit. Okay? If there's a parallel, the current does split because there's a junction, but the overall amount of current, the overall charge stays the same and comes back out on the other side. Okay? So that's how you would try to explain for both of them. Okay? Is you'd have to refer to junction rule is related to current in terms that charge must be conserved. Oops. In terms of Kirchhoff's loop rule, I'll just leave that there for now. We have what's called the loop rule, and this says that the sum of the voltage changes around the circuit's loop is zero. That is a little bit strange, so I will get rid of this conservation of energy thing. That's what it's related to. It's related to the fact that energy must be conserved. So the first section is that charge must be conserved. This is energy is being conserved. We'll come back to that. What I mean by the sum of voltage changes around a circuit loop is zero. What I'm referring to is if I have a series circuit with two light bulbs, and let's say these light bulbs are identical. If the battery is going to add 12 volts of quote-unquote electrical potential energy into the circuit. That's what a battery does. It's converting, again, the chemical to electrical potential energy. So it adds electrical potential energy into the circuit. What do the light bulbs do? What are they going to do with this voltage? They're going to split it if they're identical. This light bulb is going to take out 6 volts. What's it going to do with that? It one, lights up and it creates heat. So it's changing that energy to another form. What does this one, the second light bulb, do? It's going to also pull out 6 volts. As we said, the voltage of the components needs to add up to the total voltage coming from the battery. 6 plus 6 equals 12. But what the Kirchhoffs law is saying is while the battery adds 12 volts, both volts will take away 6 volts. So 12 minus 6 minus 6, the overall change in voltage is 0. All right, the overall change in voltage has to come out to 0. You cannot possibly have this extra volt because the idea is essentially then you just keep on adding more energy and somehow creating more and more energy, which doesn't make any sense. Okay, and so that's what the loop rule is then also relating to. The loop rule is related to the fact that energy must be conserved. Energy must be conserved. All right, because again, it's relating to voltage potential difference. It's saying the energy that's created, that's converted into electrical form, must be used so that there's no new energy all of a sudden coming from some point. Okay? So again, the battery increases the potential energy. The resistors or light bulbs reduce the potential energy. All right? And again, that explains for both situations. All right? Again, this allows us to look at circuits as loops. A series circuit is a single loop. That's easy. A parallel circuit is multiple loops. Do not ever call them multiple series circuits. That is extremely incorrect. All right? I don't know why I keep on using the word extremely. All right? But the idea is that this loop would be the same, and this loop would be the same. So that's why voltage in parallel is the same on both branches, because each one has to pull out the total voltage to complete the entire loop. Okay? So you will get questions essentially on what will happen to the overall current when another resistor is added. You might have to justify it using Kirchhoffs laws. What resistor will receive the most current or voltage through it? Again, you might have to, again, that goes back to the idea of increased resistance, decreased current, etc. And explain why the total current and total voltage of the battery is equal to the current or voltage at different parts of the circuit. That's where you're basically breaking down the whole circuit diagram and going, how much current is going here, how much is going there, etc., etc. Okay? So that's basically it. All right? Thank you.